Today we are going to continue to build up some of the theory and the basic ideas that we will be using in this later portion of the class to solve second order differential equations. Now, when we were studying first order differential equations, there were serious limitations on the varieties of differential equations that we were able to solve. We could solve linear ODEs, we could solve separable ODEs, we could solve exact ODEs, and sometimes we were lucky and we had equations that we could solve by substitution, like Bernoulli equations. Well, when we travel from the first order part of the class to the second order part of the class, the variety of ODEs that we can actually solve becomes even more restricted. Today, we will talk specifically about what's called a linear homogeneous differential equation and some of the theorems that apply to equations like that make it easy to solve them. So, a differential equation is called linear homogeneous if it has the following format. Y double prime plus p of x, some function of x, times y prime plus some function of xq times y equals, on the right-hand side, to specifically 0. This is the format of a linear homogeneous differential equation, specifically a second order linear homogeneous differential equation, because we have this second derivative here. Now, a word of caution, and something that frustrates me terribly about this class, when the word homogeneous is used in this context, the word homogeneous here is used to describe the 0 on the right-hand side of the equation. It has absolutely no relationship at all to when we used the word homogeneous back in like lesson 12 or 13 when we were talking about first order homogeneous ODEs. No relationship at all between that use of the word homogeneous and this use of the word homogeneous. So that's unfortunate. I don't make the rules, but just keep an eye out for that word is being used to mean totally different things in these different contexts. I want to talk briefly about how linear homogeneous differential equations arise naturally from many real-world situations. For example, all the way back in lesson number 1, we derived the differential equation associated with spring mass systems, where we saw that mass times acceleration was equal to restoring force plus damping force, where m was the mass, k was the spring constant, and beta was a constant associated with how much drag or air resistance your object was experiencing. So these are all constants, these are all numbers. Now let me rewrite this equation in a slightly different format. I'm going to start by pulling all of these terms over to the left-hand side. So that I have m y double prime plus beta y single prime plus ky on the left equaling 0 on the right. And then you can just as well divide out that mass, leaving you with an equation that has the exact format described when we wrote down our linear homogeneous ODE up here. We have y double prime plus some function of x alone, here the constant function, beta divided by m, and then next to y with no primes, the function q of x, once again in this context a constant function equal to k divided by m. So here we see physically a second order linear homogeneous differential equation arising from a physical context. You also get a linear homogeneous differential equation by analyzing certain circuits using, for example, Kirchhoff's law. So if you have a circuit with a capacitor storing charge, an inductor, and a resistor, but perhaps no source of impressed voltage at the moment, then when you apply Kirchhoff's loop law to a circuit of that nature, you get the following relationship between all the voltage rises and all the voltage drops in the circuit. So we know that there's going to be a voltage drop coming from the resistor. We know that there's going to be a voltage drop coming from the inductor with a magnitude of L times the derivative of the current over time. And we also know that there's going to be a voltage drop coming from the capacitor with a magnitude of 1 over the capacitance times the charge. And if there's no impressed voltage, then all of these combined will equal 0. Now, at first glance, this differential equation might not seem like an example of the kind of thing that we are talking about in this lecture, because for one thing, there's no second derivative present in what we're seeing here. And for another thing, as written, this equation currently has two output variables: the current I, which is changing over time, and the charge Q on the capacitor, which is also changing over time. However, you can rewrite this differential equation in a more standard format by remembering a relationship between the charge and the current, which is that the current is an exact match to the rate of change of the charge over time. The way I like to think about it, as someone who's not a professional in this field, is that the electrons running through the circuit are just getting stuck on one side of the capacitor, and so the electrons that are flowing through the current are directly related to how the charge on the capacitor plates changes and rises over time. So with that acknowledged, the derivative of current must be the second derivative of charge. And if I put that information into this loop equation, here in the front, L times di dt becomes L times the second derivative of charge. R times I becomes R times the first derivative of charge. And 1 over C times Q just stays put. That's equal to 0. And so now we can more clearly see that the differential equation associated with this kind of circuit is linear homogeneous of order 2, because here the function attached to Q prime is the constant function of the resistance divided by the inductance, and the constant function attached to the charge in the back is the constant function 1 over the capacitance times the inductance. So this is another example of a linear homogeneous equation arising from a real-world context. Let's describe the overall technique that we will be using over the next several days of class to help us to solve differential equations of that type. So here's a theorem that we're going to be using. We have an nth order linear homogeneous differential equation. Our focus will be on second order equations, but this theorem is true for third order, for fourth order, for fifth order, and so on. if you have a number of solutions that is equal to the order of your equation, and if all of those solutions are meaningfully different from each other, if there's no redundancy in this collection, if all those solutions are independent, then the following statement is true. You can construct every other solution to this differential equation by creating a linear combination of these first n solutions. All solutions to the ODE have the format some number times the first solution, some number times the second solution, some number times the last solution. In other words, every solution is a linear combination of these first n solution. So let's think about what this is saying to us. A differential equation in general has infinitely many solutions, infinitely many functions that make the equation true. What we're saying is, if you want to find that infinite collection of solutions to a second order differential equation, you don't have to find infinitely many solutions, you just need to find two solutions. If you can find two solutions to your second order differential equation, and if those solutions are independent from each other, then that's enough to get every other solution that exists in the world.
Editing Sam here. In other words, the two independent solutions, y1 and y2, act as primary colors. All other solutions to the second order, linear homogeneous ODE, can be obtained by mixing together y1 and y2.
So let me give you an example of this theorem in action. I have the second order linear homogeneous differential equation y double prime minus 3y single prime plus 2y equals 0. We're going to solve this equation, and we're going to solve it by starting with two functions that are solutions to this equation. I'm just going to give these solutions to us today, and over the course of the next couple of days, we're going to learn how to find these two solutions to start with. Verify that y equals e to the x and y equals e to the 2x are two solutions to the equation. To that end, I'm just going to take my two functions and plug them in to this equation and verify that both functions make the differential equation true. So here's the first one, e to the x. Y double prime is e to the x, that goes in. Y single prime is e to the x, that goes in. Y original is e to the x, that goes in. Is that equal to 0? Well, when we clean up what's on the left-hand side, we confirm, yeah, that's equal to 0. Which means that this first function is indeed a solution to the equation. Likewise, let's check the second function given, e to the 2x, first derivative 2e to the 2x, second derivative 4e to the 2x. Plug that information in, we get 4e to the 2x minus 3 copies of 2e to the 2x plus 2 copies of e to the 2x. Is that equal to 0? If we combine like terms, we get 4 minus 6 plus 2, so that's 0 indeed. So that verifies that that second function is a solution to the equation as well. Then they say, okay, so you've got these two functions which are solutions to your second order differential equation. Let's confirm that none of these functions is redundant of the other. Let's confirm that e to the x and e to the 2x are linearly independent. So I can use the Wronskian to do that. Fill up the matrix with the original functions and their first derivatives. Then calculate the determinant of that 2 by 2 matrix. I get 2e to the 3x minus e to the 3x, which is e to the 3x, and that's definitely not the zero function. So the theorem we learned yesterday verifies, okay, these two functions are meaningfully distinct. They're linearly independent. We've proven that by showing that the Wronskian is non-zero. So then someone says, solve that differential equation. At this point, we have almost no work left to do. Because we found two independent functions that make this equation true, we know that every other solution to this equation can be constructed as a linear combination of these two. So the format of all the solutions to this equation is some constant C1 times e to the x plus some constant multiple of e to the 2x. This is the format of all the solutions in the universe to this equation, just by combining these two independent solutions. Let's go through it one more time with a slightly different differential equation. Here we have x squared y double prime plus 4x y single prime minus 4y equals 0. Once again, we can see that this differential equation is linear homogeneous because if I divide all the terms in the equation by x, I see that this equation has exactly the correct format, a y double prime with a start, some function of x times y single prime, some function of x times y with no primes, and equal 0 on the right side. So this guy is second order linear homogeneous. So all I need to do to solve this equation is come up with two independent solutions to the equation, and then I know that every other solution in the universe has a format from just combining those first two. So let's verify that these two functions given to me, x to the minus 4 and x, are two solutions to this equation. And as always, we're going to do this just by plugging in. So y1 prime is negative 4, x to the minus 5. y1 double prime is 20, x to the minus 6, just using power rule. And if I plug that into the differential equation, for example, the one I've reformatted here on the right, I get 20x to the minus 6 plus 4 over x minus 4x to the minus 5 minus 4 over x squared x to the minus 4, and I want to see, does that equal 0? Well, using the exponent properties, I can clean up this expression on the left-hand side, and I could say, okay, 20x to the minus 6, then negative 16x to the minus 6, then negative 4x to the minus 6. And now I can more easily see that the expression on the left-hand side does become 0, because when I combine these like terms, I get 20 minus 16 minus 4, and 20 minus 16 minus 4 does completely cancel out and become 0. Let's do the same thing with the other given function, y2 equals x. I calculate its derivatives. First derivative is 1, second derivative is 0. And then I plug those results into my differential equation. So y double prime is 0. Then I get 4 over x times y single prime, which is 1. Then I get 4 over x squared times y original, which is x. Let's see if that equals 0 or not. But if I use the exponent properties and clean this up, on the left side, I end up with just 4 over x minus 4 over x. So here we have verified that the functions y1 and y2 that are provided to us are indeed two solutions to the equation because they make the equation true. Now let's use the Wronskian to determine if these two functions are meaningfully distinct. Let's determine if this collection of functions, x to the minus 4 and x, is independent or not. So I'm going to fill my Wronskian matrix with these two functions and their derivatives. Since I have two functions, I just need 2 rows. So now it's square, 2 by 2, we're good to go. I'll go ahead and calculate the matrix determinant using the standard formula. So I get x to the power minus 4 minus negative 4x to the minus 5 times another x. Using the exponent properties, this becomes x to the minus 4 plus 4, x to the minus 4. In total, 5x to the minus 4. And that's definitely not equal to the 0 function. Because our Wronskian's non-zero, we can conclude there's no redundancy in our collection. So our functions are independent. What this means is I have obtained the 2 pillars that I need to construct every other solution to this equation. Every other solution to the equation must be obtainable by mixing together these first 2 functions. So every other solution to the equation must have the format some number times x to the minus 4 plus some other number times x. Every other solution to this equation is a linear combination of these first 2 solutions that were provided to us. So, what this means is the process of solving a second order linear homogeneous equation boils down to finding these first 2 independent solutions. If we can find these first 2 solutions, then we can easily construct all the other solutions. And so that's what we will be doing over the next several days of class, figuring out in different situations and in different contexts the process that will allow us to find those first 2 solutions to your equation.